Today let us look at areas of combinations of plane figures. Let us look at these diagrams. If you were asked to find the area of the colored regions, the problem might seem complicated. Before we start, let us recall the different kinds of areas related to circles. Let us take a circle with center O. Now here OA is the radius. Let us take another radius OB such that angle AOB is equal to theta. We can see the minor arc APB and the major arc AQB. Now the area of the sector OAPB would be equal to pi r square by 360 times theta, where 360 is the angle subtended by the circle at the center and theta is the angle subtended by the sector at the center. Now let us draw the chord AB. Recall that we saw how to find the area of segment APB. We take area of the sector OAPB and subtract the area of triangle AOB. In order to find the area of triangle AOB, we drop a perpendicular OM on the chord AB. So the area of the triangle becomes half times base times height, or half times AB times OM. In order to find the measures of AB and OM, we prove that triangle AMO is congruent to triangle BMO. This tells us that angle BOM is equal to theta by 2. Also, AM would be equal to BM. These are corresponding parts of congruent triangles. Then we applied trigonometric ratios to the triangle BOM. So we got OM as r times cos theta by 2 and BM as r times sin theta by 2. We could substitute these values and find out the formula for area of segment APB. Now let us go back to the combinations of plane figures that we saw earlier. How can we find the area of the green region? If we add the area of yellow square to the green region, then we would get the area of this sector. Let us rearrange the terms and we get area of green region as area of sector minus area of yellow square. You could have started with this step, but it needs a little imagination. Now we could easily substitute the formulas for area of sector and area of a square. Let us look at this figure. We can see a part of a circle and a triangle. Now the part of the circle is also known as a sector of the circle. We know how to find the area of this sector. Now the other part of this figure is the area of this triangle. So if we add these two areas, then we could find the area of this combination. We could apply the formula for both these areas. Let us look at this third figure. How would we find the area of this red region? If we added the area of the blue triangular region, then we would get the area of this sector. Now we know how to find the area of a sector and a triangle. Let us look at another figure. How can we find the area of the orange region? Note that there are 4 circles in this figure. So if we added the area of these 4 circles to the orange region, then we would get the area of this square. Upon rearranging the terms, we can easily find out the area of orange region. Now look at this figure. There are 4 petals inside a square. How can we find the area of the yellow region? If we add the area of the 4 petals to this yellow region, note that the petals are formed by segments of a circle. So each petal is formed by 2 segments. So instead of area of 4 petals, we could write area of 4 times 2 segments. But finding the area of a segment is also tricky. Let us look at it another way. Let us look at the semicircles. Now let us call these 2 yellow regions as region 1 and 2. Now the rest of the square is filled with 2 semicircles. So area of yellow region 1 and 2 plus area of the 2 semicircles would give us the area of this square. Similarly, We could call the other two regions as region 3 and 4. Once again, we are adding the areas of two semicircles. But the semicircles are different this time. So this way we can find area of region 1 and 2 and region 3 and 4. Let us look at these three circles. We have to find the area of the orange region contained between them. Now this looks very complicated. We can see a triangle, but the triangle is a part of the three circles. Let us look at this a little differently. If we add area of these three sectors to the area of the orange region, then we would get area of this triangle. Rearranging the terms, we know the formula for area of a triangle and area of a sector. So we can easily find out the area of the orange region. Let us look at a few problems now. From each corner of a square of side 4 cm, a quadrant of a circle of radius 1 cm is cut, and also a circle of diameter 2 cm is cut as shown. Find the area of the remaining portion of the square. So the square has a side 4 cm, and each quadrant of a circle has radius 1 cm. Now the circle that is cut inside the square has a diameter 2 cm, which means that the radius would be half of it, or 1 cm. Now we have to find the area of the remaining portion. So how do we find the area of the green portion? If we add the area of the circle and the area of the 4 quadrants to the green portion, then we would get the area of this square. We know how to find the area of 4 quadrants. Wow! They make a circle. The circle formed by the 4 quadrants has a radius 1 cm, and the circle which was cut inside the square also has a radius 1 cm. So we could add both of them and write it as 2 times area of a circle of radius 1 cm. Now let us rearrange the terms. Apply the formulae for area of square and area of a circle. Substitute the values. And we find that area of green portion is equal to 9.71 centimeter square. Let us look at another problem. There is a racing track whose left and right ends are semicircular. The distance between the two inner parallel line segments is 60 meters, and they are each 106 meters long. If the track is 10 meters wide, find the distance around the track along its inner edge and the area of the track. Let us first label our diagram. Now we have to find the distance around the track along its inner edge, which means we are looking at the two inner parallel line segments along with the two inner semicircular arcs. Now we know that each parallel line segment measures 106 meters. So we could write that as 2 times 106. Now each of the arcs is semicircular. So the length of the arc would be half the perimeter of a circle, or 2 pi r by 2. Now we know that the distance between the two inner parallel line segments is 60 meters. So the radius of the semicircular arc would be half of that, which is 30 meters. Let us substitute the values for pi and r. Let us simplify. And we see the distance around the track along its inner edge is 400.57 meters. Now let us find the area of the track. We are looking at the area of this rectangular path. Since there are two such paths, we can do twice of the area of rectangular paths. And we have the two semicircular paths. Now the area of the rectangular path would be 2 times length times breadth, or 2 times 106 times 10. But how shall we find the area of the semicircular path? We could take the area of the bigger semicircle and subtract the smaller semicircle. Now the bigger semicircle has a radius 30 plus 10, where 10 is the width of the track. And we know the radius of the smaller semicircle is 30 meters. Now let us subtract the area of the smaller semicircle from the bigger semicircle. So pi capital R square by 2 minus pi small r square by 2. Let us take pi and 1 by 2 common and substitute the values for capital R and small r. Let us simplify. And we see that the area of the track is 4,320 meters square. Let us look at another problem. ABC is a quadrant of a circle of radius 14 centimeters and a semicircle is drawn with BC as diameter. Find the area of the shaded region. Now since it is a quadrant of a circle, angle A would be equal to 90 degrees. We are given that AC or radius of the quadrant is 14 centimeters. And we are given a semicircle with BC as diameter. Now we do not know the radius of this semicircle. And we have to find the area of the yellow region. If we add the area of segment BC, then we would get the area of the semicircle. Let us call the radius of the semicircle as r dash. So area of semicircle would be 1 by 2 times pi r dash square. Now let us subtract the area of the segment. How shall we find the area of the segment? Recall that we would take the area of sector ABC and subtract the area of triangle ABC. Let us substitute the formulae for area of sector and triangle. Area of the triangle would be half times AC times AB. Since angle A is 90 degrees, AB would act as the height. Let us take another point M. Now we know that BM and CM are also the radii of the semicircle. So both the segments would be equal to r dash. Now we can apply Pythagoras theorem on triangle ABC since it is a right angle triangle. So BC square would be equal to AC square plus AB square. Let us substitute the values and solve for r dash. It is 7 times square root of 2 centimeters. Now let us substitute the values, simplify, and we find that the area of the yellow region is 98 centimeters square.